Samsung beat TSMC to the 3-nanometer generation, rolling out a radical gate-all-around transistor design 2 years ahead of its rival. But the first chips off Samsung's 3-nanometer line didn't power a smartphone or a supercomputer. They went into a cryptocurrency mining rig. This surprising debut hints at the core mystery. Why did Samsung jump first into GAA, and is it paying off? For much of the past decade, FinFET transistors ruled advanced chips. A FinFET is like a tiny silicon fin, with the transistor's gate wrapping around 3 sides of that fin, giving better control than older flat transistors. This tri-gate design became standard at 22 nanometers and beyond, solving many issues of planar transistors. It curbed leakage and enabled further scaling. TSMC and Samsung adopted FinFET around the 16-14 nanometer nodes, enjoying years of improvements in performance and energy efficiency. However, as feature sizes approached the 3-nanometer class, FinFETs started hitting a wall. In a 3-nanometer FinFET, one side of the channel remains ungated, which becomes problematic at such tiny scales. Short channel effects and leakage currents surged at 5 nanometers and below, even with clever tricks like taller fins and multi-fin transistors. An industry expert noted that by 3 nanometers, FinFETs were offering only incremental gains. Fin height and gate length couldn't be pushed much further, and techniques like single diffusion breaks and FinFlex were the last scraps of improvement. In other words, the trusty FinFET was running out of steam at 3 nanometers. To visualize the challenge, imagine a line graph of leakage current versus transistor size. As we shrink from 7 nanometers to 5 nanometers to 3 nanometers, the FinFET curve would shoot upward due to rising leakage, whereas a new design could flatten that curve. The industry realized that beyond 5 nanometers, gate-all-around GAA transistors would be needed to maintain control. TSMC itself acknowledged that after its 3-nanometer generation, there was no more room to scale FinFET, and that a transition to GAA at 2 nanometers was inevitable. Enter GAA, gate-all-around, the successor to FinFET. GAA FETs fundamentally change the transistor shape. Rather than a fin with a gate on 3 sides, GAA devices have the gate wrap around all sides of the channel, truly gate-all-around. This provides superior electrostatic control, taming leakage, and enabling further voltage scaling. In practical terms, it's like going from holding a rod with 3 fingers to gripping it with your entire hand. The channel, rod, is fully surrounded by gate material, squeezing off current more completely when off, and driving more current when on. GAA transistors can use either nanowires, very thin channels, or nanosheets, wider, flatter channels, stacked vertically. By stacking multiple nanosheets, a GAA transistor can drive higher current in the same footprint compared to adding more fins in FinFETs. This means better performance without needing more area, and the ability to tune the channel width for each device, a flexibility FinFETs lack. Engineers had been preparing for the GAA era for years. In fact, IBM demonstrated a 5-nanometer GAA FET in 2017 and a 2-nanometer GAA FET test chip by 2021, showcasing the concept's feasibility. But bringing GAA into high-volume manufacturing is an entirely different challenge. Around 2019, both Samsung and TSMC were mapping out their roadmaps. TSMC opted to extend FinFET through its 3-nanometer node N3, delaying GAA until 2 nanometers, whereas Samsung made the bold decision to deploy GAA at 3 nanometers immediately. The motivation was clear: to leapfrog TSMC by adopting the more advanced transistor first, potentially gaining an edge in power efficiency and performance if executed correctly. Samsung's implementation of GAA is called MBCFET, multi-bridge channel FET, which uses stacks of wide nanosheet channels, like multi-bridge fins laid on their side, instead of vertical fins. Essentially, an MBCFET is a FinFET turned sideways, with the gate hugging horizontal sheets of silicon from every angle. What makes GAA so attractive that Samsung was willing to risk an early jump? Let's break down its key advantages in simple terms. Better electrostatic control. Because the gate surrounds the entire channel, it can pinch off the current more effectively when the transistor is supposed to be off. There is no fourth side for current to leak out. This dramatically reduces leakage currents and improves the subthreshold behavior of the transistor. For engineers, this means transistors can be made smaller without as much worry that they'll leak power when idle. Higher drive current. With GAA nanosheets, multiple channel layers can be stacked vertically. Samsung's MBCFET has been shown in diagrams with 3 or 4 sheets in a stack. Stacking increases the effective width of the channel, which is directly tied to drive current. In a FinFET, drive strength is boosted by adding more fins, but each additional fin takes up space. In a GAAFET, adding sheets increases drive current within the same footprint area. A single GAA transistor can drive as much or more current as a multi-fin FinFET, without eating up more chip area. Reduced operating voltage. Thanks to the improved control over the channel, GAA devices can often function at a lower supply voltage for the same performance. Lower voltage translates to lower dynamic power consumption, since switching power scales with the square of voltage. Samsung noted that MBC FETs improve power efficiency by enabling a reduced supply voltage while still driving strong current. Design flexibility. A subtle but important point. In GAA, the channel width is a design parameter that can be continuously adjusted by changing the sheet's width. In contrast, FinFETs have quantized strengths. You can only add whole fins. Samsung touted this nanosheet width adjustability as a boon for tailoring transistors to different needs on a chip. It also aids in design technology co-optimization, DTCO, finding the best trade-offs between power, performance, and area for a given chip design. In summary, GAA promised a path forward at 3 nanometers and beyond, transistors that switch faster, waste less power, and keep scaling. On paper, it was revolutionary, the antidote to FinFET's looming limitations. A promotional chart might show, for instance, FinFET versus GAA leakage power at 3 nanometers. GAA's bar would be dramatically lower than FinFET's, reflecting the gate-all-around clamp on leakage. Likewise, a graph of drive current per micron of width would have GAA scoring higher thanks to those multi-bridge channels. It's no wonder that by early 2020s, all major players knew GAA was the future. The only question was when to make the switch. Samsung made its move early. It announced in 2019 that its 3 nanometer node would use GAA transistors MBCFET instead of FinFET, aiming for initial production in 2021. The schedule slipped a bit, but by June 30th, 2022, Samsung officially declared it had started initial production on 3 nanometer GAA chips, marking the world's first commercialization of GAA at this scale. Dr. Seung Choi, head of Samsung's foundry business, lauded it as the foundry industry's first 3 nanometer process with MBCFET, claiming it defied the performance limitations of FinFET. According to Samsung, the first generation 3 nanometer process, 3GAE, gate-all-around early, could achieve 45% lower power, 23% higher performance, and 16% smaller area than its 5 nanometer FinFET node. Those are significant generational gains, on par, or better than typical node improvements, largely thanks to the new transistor architecture. Samsung even outlined a second-gen 3 nanometer 3GAP with targets of 50% power reduction and 30% performance gain versus 5 nanometer. The very first 3 nanometer GAA chips that Samsung produced in 2022 were aimed at a low-power, high-performance computing application. Industry sources suggested Qualcomm had reserved some capacity, and indeed Samsung hinted at expansion to mobile processors later. But notably, the initial chips were not for a mainstream smartphone or CPU. By July 25, 2022, Samsung held a ceremony for the first shipment of 3nm GAA chips, and the client was a Chinese crypto mining company called Pan Semi. The chip in question was an ASIC for Bitcoin mining, a pipe cleaner product to test the new process with a real design but relatively low risk. Industry analysts later revealed why this made sense. Samsung's 3nm SF3E process, the early version, was used to build a crypto mining ASIC, MicroBT's WhatsMiner M56S++, which contains no SRAM memory on-chip. By avoiding on-chip SRAM, Samsung simplified the process complexity. SRAM cells are often the hardest to yield at new nodes. In essence, Samsung played it safe with its first GAA implementation, choosing a chip without dense memory structures and for a client that could tolerate lower initial yields. It was a strategic way to start, get something out the door to claim first GAA title, learn from it, but not risk a high-profile customer product on a nascent technology. Samsung's marketing proudly proclaimed a 2-year lead over TSMC and 1-year lead over Intel in bringing GAA to market. Indeed, TSMC's first GAA won't arrive until its 2nm node in 2025, and Intel's FinFET, its GAA flavor, is scheduled for 2024 with Intel's 20A process. Samsung clearly hoped this head start would translate into a tech leadership advantage, being first to the future of transistors. From Samsung's perspective, this was a bold gamble to regain ground in the foundry race. By 2022, Samsung's foundry market share had been languishing in the mid-teens %, far behind TSMC, which had over 50% of the market. Samsung had also suffered some high-profile setbacks at 5nm/4nm nodes. For example, yield issues on Samsung's 4nm reportedly caused Qualcomm to switch its flagship Snapdragon chip manufacturing back to TSMC in 2022. Internally, Samsung leaders saw an opportunity. If they could leap to GAA ahead of TSMC, they might attract customers who crave the latest technology or who need the power efficiency gains. It could reshape the competitive dynamics, positioning Samsung not as a follower, but as a trailblazer in the post-FinFET era. However, first doesn't always mean best or easiest. Implementing GAA at 3nm was technically arduous. Samsung had to integrate brand new device structures into a process flow that also included other cutting-edge techniques like EUV lithography, extreme ultraviolet lithography, introduced at 7nm. The complexity is immense. Nanosheet FETs require precise etching to form the sheet stacks, new workarounds for spacing and variability, and robust design tools to model these devices. In retrospect, Samsung's 3nm gamble was akin to jumping 2 hurdles at once. The normal challenges of a new node shrink, plus the challenges of a new transistor architecture. Soon after Samsung's 3nm launch, rumors emerged that things were not rosy in the fab. Initial yield, the percentage of working chips per wafer, was abysmally low. Early reports suggested in the 10 to 20% range. To put that in context, TSMC's 5nm and early 3nm yields for big customers were often 70% or higher around that time. A yield of 20% means 8 out of 10 chips were coming out defective. Fine for a research experiment, terrible for mass production economics. Samsung didn't publicly confirm numbers, but by late 2022 and early 2023, it was clear that no major consumer product was being built on Samsung 3nm. Major fabless clients stayed on the sidelines. Nvidia, Apple, AMD, MediaTek, Qualcomm, even Samsung's own mobile division, all stuck with TSMC's 4nm or 3nm FinFET processes for their leading chips. A news report in mid-2024 noted that 7 big customers, Apple, Qualcomm, Nvidia, AMD, Intel, MediaTek, Google, had all prioritized TSMC's 3nm, despite Samsung's head start. Notably, Google had been making its Pixel Tensor chips at Samsung 5nm. but decided to move to TSMC for the 3nm generation, and Qualcomm's Snapdragon 8 Gen 4 is likewise expected on TSMC 3nm. Why the cold shoulder from customers? The data points to yield and performance issues on Samsung's 3nm GAA. Samsung officially started mass production in summer 2022, but through 2023 it struggled to secure any high-volume orders. The first Gen 3nm node, called SF3E or 3GAE, remained stuck in low-volume niche production, essentially that crypto ASIC. Even Samsung's own Exynos 2500 chip, which was being developed on 3nm, faced yield problems so severe that it reportedly delayed the chip. Samsung's mobile division ended up going with Qualcomm Snapdragon chips, rather than risk an underperforming Exynos. Industry experts cited poor yield and even subpar power efficiency as the main issues with Samsung's 3nm. That's right. Despite GAA's theoretical advantages, analyses indicated Samsung's 3nm was still 10 to 20% behind TSMC's equivalent node in performance. Apparently, the combination of design choices and low yields forced Samsung to use lower-performing silicon, or lower clock speeds, to get chips out, undercutting the benefit of the technology. One big customer bluntly stated that the reason they choose TSMC is the better power efficiency of TSMC's chips at the cutting edge. TSMC's reputation for stable and dependable manufacturing made it worth even a 25% higher price per wafer at 3nm. By late 2023, Samsung claimed improvements. There were reports that first-gen 3nm yields climbed to approximately 60%, a significant jump from the initial state. But this took well over a year to achieve, and in that time, Samsung had lost out on billions of dollars of potential business. Worse, the second-generation 3nm, presumably the refined 3GAP process, was not doing well at all. As of late 2024, its yield was rumored around 20%, barely a third of the internal 70% target. Such numbers cast doubt on whether Samsung could ramp 3GAP quickly for, say, a Galaxy phone processor in 2024/2025. No surprise, then, that Samsung's only known 3nm product shipping in 2023 was still that crypto miner ASIC. Tech Insights literally had to hunt down a microBT mining rig to find Samsung's 3nm chip inside. Meanwhile, TSMC started volume production of 3nm's FinFET in Q4 2022 and was reliably serving Apple and others through 2023. Apple's A17 Pro chip in late 2023 iPhones used TSMC N3, and though TSMC faced its own yield learning curve, it was a low-risk evolution of familiar FinFET tech. Apple, Nvidia, AMD, none chose Samsung's GAA 3nm, despite the allure of a potentially superior transistor. For them, a stable 3nm from TSMC beat an unproven 3nm GAA from Samsung. From a market standpoint, Samsung's early GAA bet did not translate into immediate leadership. In fact, Samsung's foundry market share continued to erode during this period. A bar chart of foundry market share from 2020 to 2024 tells the story. Here's a foundry market share comparison. Samsung's slice shrank from approximately 17% in 2020 to approximately 10% in 2024, while TSMC grew from approximately 54% to approximately 64%. Samsung's bold technology move wasn't enough to win customers' trust against TSMC's track record. By Q1 2024, Samsung's global foundry share actually fell to 7.7%, its lowest on record, while TSMC reached 67.6%. In other words, TSMC was shipping the majority of the world's leading-edge chips, and Samsung was left fighting over a small fraction, along with other players like GlobalFoundries, UMC, and SMIC. Samsung had bet on GAA to be a differentiator, but it became a liability in the short term, an expensive technology with few takers. As one commentary put it, Samsung may be the high-risk taker, but it backfired. TSMC's cautious approach shows dominance. It wasn't just external customers. Within Samsung's own semiconductor divisions, tensions arose. The System LSI division, which designs Exynos chips, was counting on the 3-nanometer process for its next SoC, but as noted, those plans faltered. Samsung's smartphone business ended up using only Qualcomm Snapdragon for the Galaxy S25 generation, because the Exynos 2500 on 3 nanometers wasn't ready in sufficient volume. These internal struggles highlighted a broader issue. Samsung's foundry had to rebuild trust. Years of under-delivering on promises, from 14-nanometer yield hiccups to 4-nanometer throttling issues, and now 3-nanometer delays, made clients wary. As an industry saying goes, innovation means little without adoption and mastery. Samsung learned this the hard way. Being first to 3-nanometer GAA brought more skepticism than design wins. Samsung's head start is not permanent. The competition is fast approaching the GAA era, but with the benefit of learning from Samsung's trials. TSMC's 2-nanometer node, N2, will introduce GAA FETs, likely nanosheet-based, similar to Samsung's approach, and is scheduled for risk production in late 2024 and high-volume 2025 manufacturing in 2025. TSMC has been conservative, extending FinFET through N3 and its enhanced versions, N3E, N3P, etc., squeezing out as much as possible with incremental improvements. This gave TSMC time to mature EUV and other process steps before layering on the GAA transition. When N2 arrives, TSMC is also adding backside power delivery, a technology to deliver power via separate metallization under the silicon, reducing IR drop, making their 2-nanometer a big leap in multiple ways. TSMC's expectation is that by moving to GAA slightly later, they can achieve smoother adoption, essentially avoiding some early pitfalls Samsung encountered. As one report indicated, TSMC's careful approach aims for smoother adoption, having observed Samsung's challenges. Intel, on the other hand, is jumping to GAA in its own timeline around 2024 to 2025. Intel calls its GAA transistor ribbon FET, and it's planned to debut with the Intel 20A node, which Intel equates roughly to 2-nanometer class, in 2024. Intel 20A and the follow-on Intel 18A, 1.8 nanometers, will both use ribbon FET, along with an innovation called Power Via, Intel's version of backside power. Intel's roadmap, if on schedule, could actually beat TSMC's 2 nanometers by a bit. Intel claims volume production of 20A in 2024 and 18A in 2025. However, Intel's execution in recent years has struggled, so the industry remains cautious about those timelines. Still, Intel is positioning ribbon FET as a chance to regain process leadership if they can pull it off by 2025. Intel has even snagged some foundry customers to use 18A, indicating confidence in its competitiveness. So by 2025, all 3 big players should be in the GAA game. Samsung in its 2nd-gen GAA, and possibly starting 2-nanometer development, TSMC with 2-nanometer GAA FETs ramping up, and Intel with 18A ribbon FET in production. A timeline chart of GAA adoption would show Samsung planting its flag at 2022, 3-nanometer GAA risk production, Intel around 2024, 20A ribbon FET, and TSMC at 2025, N2 GAA. Samsung's lead, which was once 2+ years, will effectively shrink to 0 as everyone converges on GAA by 2025. The question then becomes, did Samsung's early gamble give it a lasting advantage, or did it simply force Samsung to be the beta tester for GAA technology that others now implement more smoothly? There are some silver linings for Samsung. Having fought through one generation of GAA learning, Samsung could be better positioned for the next. Reports suggest Samsung is diverting resources to focus on its 2-nanometer GAA node, planned approximately 2025 to 2026, determined to fix the mistakes of 3 nanometer and not fall further behind. In July 2023, TechInsights confirmed Samsung's 3 nanometer was indeed working in silicon, the microBT minor, demonstrating they overcame many integration issues. And though customer adoption was minimal at 3 nanometers, Samsung can now offer GAA experience that TSMC is just starting to gather. In other words, Samsung took a painful first step so that its second step, 2 nanometers, might be on firmer ground. Meanwhile, TSMC and Intel will have their own GAA hurdles. TSMC's 2 nanometer is introducing new materials and that backside power, which is itself a significant process change that can bring yield challenges. Intel's FinFET and PowerVia are unproven in high volume, and Intel is essentially trying to leapfrog from a 4 nanometer class node, Intel 4/3, to 2 nanometer class with 2 new technologies at once. If Intel slips, it may not threaten TSMC as hoped. For Samsung, any fumble by the others is a chance to catch up. One interesting note: there are already murmurs that TSMC's early 2 nanometer RISC wafers are facing some process instability issues, though it's hard to gauge from outside. If true, it underlines that GAA is a challenging transition for everyone, not just Samsung. All said, the race at 2 nanometers and beyond is now a more level playing field technology-wise. All will be using GAA transistors and EUV lithography extensively, so the differentiators may come down to execution, yield, cost, and perhaps packaging innovations. Samsung's dream is that by being first with GAA, it will benefit from a more mature technology in the second generation, and maybe lure back a big customer or two if TSMC or Intel hit a snag. From a pragmatic view, some critics argue that Samsung pulled the trigger on GAA too early. The manufacturing cost of a bleeding-edge node is astronomical. Adding a novel transistor structure only inflates it further. An analysis in 2021 warned that the transition to GAA would likely be the costliest yet, and indeed, not many foundries, besides the big three, could even dream of affording it. Samsung invested heavily in new equipment and R&D for GAA, but if the yields are low, the cost per good chip is extremely high. Each wafer at 3 nanometers can cost several $1,000s to process. At 20% yield, the effective cost per chip is 5 times higher than at 100% yield. This erodes the economic viability of the node for customers unless fixed. There's also the risk to reputation. By advertising world-first 3 nanometer GAA and then not being able to deliver volume, Samsung may have undermined confidence. Some in the industry framed it as a classic technology push without sufficient product pull. If no major product is using your tech, being first is a Pyrrhic victory. Additionally, Samsung's early GAA might have inadvertently exposed the technology's challenges under the public eye. TSMC and Intel got to watch Samsung's GAA struggles from the sidelines, adjust their approach, and maybe avoid the same mistakes. For example, ensuring better design tool readiness, focusing on simplifying initial IP blocks like SRAM, etc. In effect, Samsung shouldered the burden of debug and pathfinding that others will leverage. From the design perspective, a new transistor means new design IP, new EDA tool models, and relearning by engineers. One reason Apple likely stayed with TSMC N3 FinFET was to reuse much of its 5 nanometer IP and design flow, a known environment. Adopting Samsung 3 nanometer GAA would require requalification of libraries, memory compilers, and IP blocks for GAA, with the risk of bugs. For companies on tight product cycles, that risk wasn't worth it in 2022/2023. This highlights a wider point. Cutting-edge nodes need a robust ecosystem. Samsung's ecosystem, the safe partners as it calls them, work to provide design tools for 3 nanometers, but it takes time to build confidence in those. there were reports that Samsung's 3nm had immature EDA support initially, leading to design difficulties. TSMC's conservative approach gave EDA vendors more time to catch up for 2nm. Another counterpoint is that not every chip needs GAA at 3nm. Many products can meet power and performance targets at 5nm or 4nm. By rushing to 3nm GAA, Samsung was targeting a narrow slice of the market, ultra-low power or highest performance chips, which in 2022 to 2023 was basically smartphones and a few CPU-GPU designs. Those were all taken by TSMC. The broader market, IoT, automotive mid-range SoCs, was not ready to pay premium for 3nm. Thus, Samsung built a race car track before many racers had cars to drive on it. TSMC, by contrast, made a fortune selling its well-oiled 5nm and 4nm while carefully readying 3nm. One can also ask, if Samsung had stuck with FinFET at 3nm, like a hypothetical Samsung 3nm FinFET, might it have fared better short-term? Possibly yes. They could have iterated on a known architecture and maybe achieved acceptable yields faster. But long-term, that would only delay the inevitable shift to GAA, and Samsung would be back in the position of playing catch-up with TSMC. By biting the bullet early, Samsung at least positioned itself as a pioneer, which has intangible value for attracting talent and partners. The best semiconductor engineers want to work on the newest tech.